quantum technology, which currently only has a handful of applications. Like I said, very niche things. Wouldn't it be great if more and more people were thinking about how to use it and they came up with applications the scientists wouldn't even think of?
Welcome to the Emergence Podcast, where we discuss ideas that have emerged from collaboration and interdisciplinary work in the physics department at the University of Illinois.
Illinois physics professor Gina Lorenz received her BA in physics, magna cum laude, and mathematics, and completed her PhD in physics at the University of Colorado at Boulder. She was then a postdoctoral researcher in the Department of Atomic and Laser Physics at the University of Oxford. Her next position was an assistant professor in the Department of Physics and Astronomy at the University of Delaware. She joined the Department of Physics at the University of Illinois at Urbana-Champaign in 2015, where her research group performs experiments in quantum optics, atomic and molecular spectroscopy, and optical magnetometry. In 2023, her research group, in collaboration with a group of Paul Kwiat and university and community partners, launched the first publicly accessible quantum network.
Yes, welcome, Gina. Thank you so much for coming on.
Thank you so much. Look forward to this.
Yeah.
So, what happy accidents and strategic choices got you to this point in your career?
Yeah, a lot of research is unpredictable. I mean, that's partly why we do it. It's exciting. We have these questions and they lead us down paths that we don't necessarily expect. And so that definitely was the case for my career. I would say as an undergraduate student, I was not fully aware of kind of physics research and what was possible. But I wanted to have the opportunity to have that experience and also get some credit for that as an undergraduate. So there was a program at CU Boulder where you could get matched with a group and do undergraduate research. And as soon as I started working in the lab, I thought, this is really great. Because before, you learn all these concepts and principles and they're kind of abstract. And then you go in the lab and you just see, wow, you get to work with lasers. You get to, work with these new technologies that can be built from scratch. You understand how it's all working. And I've always enjoyed working with technology. My dad, he was, he taught for the Department of Defense overseas schools, and he brought those Mac 2GSs to the elementary and middle schoolers that he taught, and they got to work on these first personal computers, and I was so like really excited. And I just loved working on those new devices. Like, this is amazing, and then, dot matrix printers and all of that technology. And so, all of us have experienced kind of the ramping up of this. And, it's accelerating in terms of, the number of things you can do with a phone, for example. So yeah, that's how my interest really got sparked. And then from then on, I just wanted to continue, basically. Of course, there are certain, junctures where you have to make a decision what exactly you want to do. And I still was open to other types of topics. But at the end of the day, I'm still here. So yeah, I'm still really engaged and excited by, research and technology. So
yeah, that's awesome. And what was when your interest really got sparked at Boulder, what was the project that you were working on there?
So that is another thing. When I went into the PI's office, he said, I'm working on the Lorenz shift. I was like, it's like the first sentence he said or something. And I was like, well, obviously that's what I have to work on. And so, but then it was dealing with atomic vapors. So, you put water on a stove and you heat it up and there's this water vapor that forms above it. Same thing happens with any element. And the element we were looking at was potassium. Potassium is a metal that's as soft as peanut butter at room temperature. And we put it in a cell, which is just a metal glass kind of encasement that allows you to heat it up, like heating up water on a stove, and create a vapor. And here it's a vapor of potassium atoms and some potassium molecules. And then you can shine a laser on that gas of atoms, and you can start to learn about what's happening to the atoms as they collide with each other. And so we were looking at when you excite an atom. So you have the light and it interacts with the atom. The electrons gain energy. So they take the incoming light and transition to a higher energy level in the atom. And we looked at those transitions and how they were affected by collisions, and also the degree to which the effects of those collisions could be reversed or not. So this had to be reversible and irreversible dynamics is what we called it. And we were able to do this in a way using really, really short pulses of light. So ultra short pulses, that's, 10 to the minus 12 seconds, really, really short pulses. And at that point, you think you go to a dance party, they turn on the stroboscope and you can kind of see this cool effect, right? Where you're moving, but you see little snapshots of it. That's basically what we were doing in the lab. We're taking snapshots of the atoms at various timescales and seeing how the dynamics influenced kind of the electrons and what states they, what frequencies they would be at and so on. So that was really neat, to do kind of ultra fast spectroscopy is the kind of name of that field. And that's where I started. Yeah.
Mm-hmm. Awesome. Very cool. Yeah, I can very much relate to the love for. I remember joining like one of my first undergrad labs, and it was just so fun to see like the concepts in your physics courses like, kind of coming together.
Yes.
And you like. I think the thing that I love the most is that you can kind of start to trust what you learned in the courses because you can see them right in front of your eyes.
Right. Yeah, they take on a relevance because you're like, if I don't get this right, then it won't work, or something disastrous might happen in the lab, if you don't. Yeah. And it's like, oh, this actually is real. It actually does matter. That factor of 2 can make a difference, And so, absolutely.
I feel like in like several fields of physics are pretty esoteric. Mm-hmm. It's not like you sort of kind of go out into your backyard and you're an ecologist and you kind of see how that community changes throughout the seasons and stuff like that. Like lots of fields of physics are pretty esoteric. So to actually have that grounded in a thing you can see.
Absolutely. Yes.
It's very essential.
And some of the things you see are just beautiful on their own right, because the glow of the potassium atoms was pink. And, and then as they're heating, they kind of make these little bubbles on the surface of the sapphire glass. And I don't know, it's just, there's a lot to gain from just the aesthetics of being in the lab, and just, it's just really cool to work with such neat things.
I can totally relate to that. Even like the chords, there's so many chords in lab, and for whatever reason, I've gotten like an aesthetic taste for just like the chords, the different colored objects, all of these things.
Right. Yeah. And I think that's part of the trade, right? Yeah. I mean, I think anyone who gets really immersed in something, it's like they have a taste for, not that particular thing, but this is the good one, And I think it's the case in the lab as well. So,
yeah, that's awesome. So kind of talking a little bit more about your current work as a faculty member. So your work right now builds upon the fundamental quantum principles of superposition and entanglement. Can you kind of explain these principles for our listeners?
Right. Yeah. So, this came about in part because we have a new kind of wave of funding nowadays for quantum technology. And that's quantum technology that is based on superposition and entanglement. And so that's often referred to as quantum 2.0. So quantum 1.0 is the sort of stuff we have in our computers nowadays. You can go to the supermarket and have a laser that you check out with, and you have transistors and things like that in your computers. And those are all, they use some elements of quantum mechanics, like quantization, tunneling, and that sort of thing. But the kind of quintessential aspect of quantum mechanics that distinguishes it from the classical understanding of the world is entanglement. Mm-hmm. And so quantum 2.0 technology uses entanglement. And the types of things you can do are quantum computers that allow you to solve problems that would otherwise be intractable for a classical computer. You can do quantum sensing using entanglement, such as improving astronomical imaging. And then you can also do quantum networks. Now, quantum networks, they allow you to connect to distant quantum computers. And even on their own, though, even if you don't have a quantum computer, they allow you to do things like completely secure communication. Because entanglement, it's interesting, what entanglement is two quantum particles can be correlated, no matter how far apart they are. And, one example of an entangled state is they're correlated such that you measure one to be, polarized or moving up and down. And as soon as you make that measurement on one particle, the other particle becomes that same state. Now, I've kind of gotten ahead of myself a little bit because I like to start with superposition. So, entanglement is a type of superposition. Entanglement is a superposition that involves more than one particle. Mm-hmm. But if we just back up a bit and talk about what superposition is. So, superposition is related to the fact that you have some quantum particle and its state can be indeterminate. So it could be, in the case of light, it could be oscillating up and down. It could be oscillating right and left. But until you make a measurement, until you actually check what state it's in, it remains uncertain, undecided between those two options. Mm-hmm. So that's what we call a superposition. And then if you have two such particles, they can be entangled such that measuring one influences the other. Mm-hmm. So they're correlated so that no matter how far apart they are, when you measure one to be a certain state, the other automatically becomes that state. So that's superposition and entanglement. And then you can use that for secure communication because, and you can kind of imagine this, you have two particles that are entangled and you keep one with you and you share the other one by sending it in, either through the air or through an optical fiber to someone else. And if there's someone along the way that intercepts that photon, that particle of light, and they make a measurement, they will cause the photon to be in a particular state. Mm-hmm. And if you choose to make measurements in certain ways, you can actually detect when that's occurred. Mm-hmm. So even if they try to copy it and send it on, you can choose to make measurements such that you can detect whether there's an eavesdropper present. Oh, okay. And yeah, I'm kind of glossing over a lot of details, but I just wanted to give the overall picture of what superposition and entanglement are and how they can be useful.
Yeah. Awesome.
Yeah, that's awesome.
Can you give any more examples of promising quantum 2.0 technologies?
Yeah, so I guess I've talked about secure communication, and I briefly mentioned sensing applications. Mm-hmm. And so just focusing on the quantum network side of things, quantum sensing can be improved with a quantum network. So if you've paid attention a few years ago to the news around the imaging of the black hole, mm-hmm. That was obtained through many telescopes distributed all across the world. And they recorded the waveforms of the incoming light mm-hmm. from that astronomical object. And then by combining those waveforms a certain way, you can generate the image. Oh, okay. And that allows you to take really high resolution images of very, very distant astronomical objects. That was all at radio wavelengths. If you wanted to do that at optical wavelengths, then you would have to find a way either to record the optical waveforms, which we currently don't have a way to do because they're so high frequency, or literally send the photons, send the light and interfere them between the different telescopes. Oh. And so the way they do astronomical imaging in the optical regime with this interferometric technique is to actually send light between the telescopes. But they experience loss. And if you want to scale that up, so currently it's like 300 meters between telescopes. Mm-hmm. If you want to scale that up and achieve higher and higher resolution, you'll get more and more loss. Mm-hmm. And so there's a proposal that says if you have a photon that you create on Earth, and so it's not the stellar photons, it's what we call the terrestrial photons, right? So you create a photon and you send it to two telescopes. You don't know which telescope it will go to, and have that photon interfere with the light coming from the astronomical object. It's equivalent to sending the photons from the two telescopes and interfering them. And what's nice is if you have a high enough rate of creating that terrestrial photon, then you can overcome the loss issues associated with that distance. Yeah.
Oh, okay.
Yeah.
That's really
Okay, gotcha.
fascinating.
Yeah.
So, so just for my own understanding, so you have multiple kind of stations around the globe trying to make a measurement of some astronomical object, like a black hole, that's many, many light years away. And they can take those images in radio waves, but they, in order to take those images in optical, so like the visible light that we see every day, they need to I guess which photons are interfering with each other?
Yeah. So the photons received from the astronomical object are, in the case of radio waves, they're recorded, and then the waveforms are digitally interfered with each other. And they can do that. Yeah. And so, whereas optically, we have no way of recording an optical waveform. It oscillates too quickly.
Okay.
So there's no way to get the phase information, which is critical to interference, to see. Yeah, I don't want to get too bogged down in the details, but it's kind of like a Fourier transform. So the spatial position of the light that came from the astronomical object can be determined by basically doing measuring it at two locations and looking at the relative phase of the light received by those two locations.
Okay, makes sense.
Yeah.
Makes sense. Yeah.
And so optical waveforms can't be recorded. So how do you interfere them? Well, you literally send them to each other. But then you have to traverse the distance between the telescopes. And then because of loss of the photon, you can only go so far. And so the idea is have a resource on Earth where you have another photon, and that photon is in a superposition actually of being between the two telescopes. And by interfering that photon with the light from the star at the two telescopes, you can do the same thing, except now you're not limited so much by the distance. You can increase the distance. Yes.
That is so cool.
Yeah. It's cool because it's like astronomy, and then it's like a network that's spanning distance. So it's like, whereas in the lab, quite often we're thinking really small, and quite often with quantum, you'll hear it's the very small and the very cold. What's great about photons is it doesn't need to be cold. And it can be big. Yeah, it can be the size of the internet, basically, once we get to that stage, of course. Yeah.
And what is the reason that it needs to be cold?
So usually when people are saying that it needs to be cold, they're thinking of matter-based systems. So single atoms, superconducting qubits, just in the name itself, it implies cold, so superconducting. Any kind of material system, to get it to exhibit those properties of superposition and entanglement, and have it stick around long enough to measure it and not decohere immediately, you need to cool them down, because you'll have collisions, you'll have thermal excitations of the atoms, and all of that can, degrade the degree of entanglement that you want. And so, the quantum computers that are being built, they rely on cooling the atoms and the circuits so that they work in the quantum regime. Whereas photons, they don't interact readily with the environment, so they don't lose their coherence readily. They can be sent through a really thin strand of glass that we call an optical fiber over a really long distance. And you can, of course, they might, rotate their polarization. They might get lost, and that's kind of the worst thing that happens is they get lost, they get bounced off, and they're no longer guided. But it's amazing. You can still get quite good rates in terms of how many photons you can send from point to point. And you can adjust at the end what may have happened to distort the state of the photon, but it's still there and it's still coherent, and you can still do something with it. And that's all room temperature. You don't need anything cool. And what's also great, and this is part of what my group did, is you can just use optical fiber that's already in the ground, that's used for the internet. So, you don't need anything special in terms of new infrastructure. Of course, to make it really, really good, then sometimes you might want to make more specialty fiber and stuff like that. But as we demonstrated, even the fiber that's in the ground already can take you from a lab on a campus over to a public space and have people interact with the photons there.
For listeners, when we say coherence, we mean sort of like it kind of has the quantum properties that we're interested in. And when we say decoherence, then it's kind of lost the quantum properties of interest. If that's
yeah, that's right. You can think of waves in water, and you drop a little pebble in water and you see this kind of concentric circles going out. And then if you were to like slap the water or put another pebble in, it would cause it to lose some of that nice, smooth oscillation. Mm-hmm. And that's decoherence.
Just to go back to the images of astronomical objects, is there, could you give an example of like an object that quantum could image better, or like something that, like an image that could be improved on?
Yeah, and I'll just say, this is really at the cutting edge in terms of like the proposal itself is not that old. It's, I think 2010 or 2011. And the research around it has brought up all kinds of issues like, okay, in what limit will you actually see an advantage? And when you get to these larger distances between the telescopes, you also, you may get higher resolution, but you'll get fewer photons per frequency bin. Or like if you were to slice up your frequency space into tiny little slices, then you get less light per slice. So, it doesn't come at the cost of nothing. There's trade-offs. Mm-hmm. And so, we've looked into it quite a bit, and it turns out it has to be a relatively bright star. And I think we have identified one, but we haven't published it yet. And I don't want to say because we haven't fully, but, there's definitely like a range, like a narrow range over which you can show quantum advantage. Mm-hmm. And this is always the problem, right? In quantum information science, people ask, what can you do? And it's like, well, in this really specific situation where you have this number of parameters and so on. And if you consider, what are you comparing against? Let's talk about what you're comparing against. And so there's a lot of caveats around it. And so, and it's no different for quantum sensing. Actually, for quantum sensing, it's probably even worse in certain, because if you blast something with enough light, usually you can make up for any deficiencies and loss and so on, right? Yeah. And now when it comes to and it's kind of the same idea for astronomical sensing. You can, for the brightest stars, you tend to be able to see at higher resolution, which makes sense. You have more light to work with. And so you're just trying to find that regime where it's not as bright maybe as you would need it to be to do it classically, but we can do it quantum mechanically. Yeah. So, right? So you just have to find that regime.
Gotcha.
Yeah.
I want to ask a question that kind of branches off of that a little bit. Many use cases for quantum 2.0 are kind of largely unknown. And we need a lot of input from other disciplines to find these use cases. And as you mentioned, they can be kind of narrow, can be kind of hard to pin down when you can get a quantum advantage. Mm-hmm. So I was wondering, how can someone from a different discipline learn about quantum 2.0 and learn how to apply it to their work? Yeah,
I think everyone has something to bring to it. I personally think that we have just gotten the tip of the iceberg in terms of what is possible. And I think there are many angles you could take. There's kind of the practical angle where you look at what protocols are already out there, and then you think about implementing them in new ways. And then I guess, in a way, the public quantum network that we're going to talk about is one example of that, where we didn't really change the technology so much. We just applied it in a new way, in a new arena. And then it raised more questions about how to fix these problems. You could also think it from a fundamental or a foundational perspective. And, I think there's still quite a bit of work to be done at the fundamental level. And that might just be, you might pick a particular platform that you already have a lot of expertise in, like material science, and you're really good at making certain things. And then you find a niche where, hey, my technique actually would be useful for that quantum computing platform. And so I think, and a lot of times this is what happens. Scientists in a different field, they'll see, you happen to overlap with me right here. And actually I have a lot of stuff I can do to improve what you do in that space where we overlap. So I would call that kind of fundamental level sort of things. And then there's the foundational element, which I think is under researched. And it has to do with kind of the underlying meaning.
Yes.
Which, honestly, everyone wants to understand this, right? And if you keep probing a physicist, eventually you're going to get to a quantum interpretation, whether or not that physicist is aware that they are using an interpretation. And I think there needs to be a lot more light on that area to bring it to the undergraduate level even. It's not even at the undergraduate level in terms of training to know what theories are out there that can kind of give some idea of what might be going on beyond what we currently understand. So what is causing entanglement? What is the mechanism for entanglement? It's really fascinating. And I think it actually draws more attention if you start to address that than if you just say practical technological things for some people. I think everyone's different, but almost every time I do outreach, everyone asks that foundational question. And I myself am doing some remediation of my own academic training and trying to I should read up on that. So I have a more complete answer for them. Then I can point them in different directions where to learn more. I could go on and on about that element of things. But just one example is, people see in the Marvel movies and so on, they see quantum interpretations right at play. They see many worlds happening, Ant-Man and so on. And that's just one perspective. And there are many fascinating perspectives that you could have on what could be actually going on. And I think there's a hesitancy to lead any physics student down that path because there's not much funding.
Yes.
And, but I think the more and more quantum technology is in kind of the public awareness, the more we're going to have to address it. And so more physicists should be ready to address it. And I would be excited to see more physicists study it because I think there are things we can test and the more that people think about it, the more ideas we'll have.
So is it just for clarification, the more that we understand about the foundational, for instance, what the many world interpretation, or not many world, what the quantum interpretations are, the more kind of applications that we can provide?
Potentially. So I guess I see it as a paradigm shift. You go through something in your life and suddenly you're like, oh, I just see the past events differently. Or if I see from this person's perspective on my problem, I never would have thought of doing it that way. But because I saw what this person's doing, I'm going to try it. Okay. It's out of the box thinking. Okay. Because, I think quite often we think this is it. We've seen it from all angles, but we are still in a box. And I think that's definitely the case for physics, especially, we're basically doing the Copenhagen interpretation in the lab. Yeah. And that's fine. But if you really think outside of that a little bit, you might think of experiments that you never would have thought of otherwise.
Okay.
Either to test the theories or just because you're thinking differently. You're not thinking in terms of wave function collapse. You're instead thinking in terms of entanglement being extended to your measurement devices. And that might lead you to doing a different way than you would otherwise. It's just...
Yeah, that's very true. Yeah, we definitely... So we're kind of talking about... so we have these quantum mechanical properties like entanglement that we've touched on, and then there are also different interpretations of what is like the mechanistic driver, what's happening. So they mentioned the many worlds theory, or the many worlds interpretation, which is, of course, correct me if I'm wrong, but when you have a particle in the sort of indeterminate state of it's oscillating up and down, and it's oscillating side to side, and you don't know which direction it's oscillating in until you measure it. In the many worlds interpretation, once you measure it, there's one world where it's oscillating up and down, and one world where it's oscillating side to side.
Yeah.
And you have just kind of entered one of the forks.
Right.
And so when like folks like Gina and Mari are doing quantum mechanics in the lab, they're sort of operating on one sort of paradigm of the mechanistic drivers of these kind of quantum mechanical properties, and there's not really a strong initiative to really like kind of question that paradigm.
Yeah, exactly. Very well put.
Yeah.
Yeah, and I really like your argument for, it might make you think differently. I think human creativity and scientific creativity is something that, I don't know, it feels very anomalous.
Yeah.
And I love the idea that like taking seriously a different paradigm might lead you down a completely different path. I think that's just really fascinating.
Yes. So do I. I mean, and honestly, this is new for me. I didn't really think about these things too much until the last year or so. So I'm definitely not the expert on this, but I'm so fascinated by it. I can't stop talking about it.
And was it sort of the interacting with the public and their questions that kind of got you along?
I think that was a big thing.
Yeah.
Absolutely. And actually it was on a radio show up in Chicago. So Paul Kwiat and I were on a radio show, and it was Turi Ryder, and she asked us this question. She said, my father was a mathematical economist, and he always used to say that the thermos was the best invention because how did it know whether to keep things hot or cold? And then she said, how do the photons know, the entangled photons, how do they know what to do when one is measured? And there was radio silence. As I grappled with the fact that at that moment, I thought, I really wish I had in my pocket right now that wonderful synopsis of all the different theories and their implications.
Yeah.
And I missed that. But at the end, we just said, that's a great question. That's still an open question. The scientists don't know. And I said, and that's partly why we want more people to be interacting with this so we get more diversity of thought around these questions.
Yeah.
And so, I kind of used the question to boost what we were doing, but I do believe that. And then I went and was like, I got to get some books on the topic and start building up my resource of being able to answer in a way that I would be more satisfied with. So definitely.
Yeah, I think it's wonderful because that's the kind of question that really pulls people in.
Exactly. Yeah. Well, she's a great. So are you all. You've all pulled us here. So
yeah. And could you give us kind of like a brief overview of like the different interpretations for how they know?
Well, I'll just give you one other one because I'm not prepared to do the others. I'm still in my mode of research in that area. But one of them is Bohmian mechanics. And so this is David Bohm. It's really, once you start reading his works and so on, you can't help but be pulled into his story, as a person. Mm-hmm. So this was back during, the making of the atomic bomb. So he actually was a student of Oppenheimer. And some of his work even became classified that he did with Oppenheimer. But he also had slight interests in kind of left-leaning sorts of ideas. And so he ended up having to leave the U.S. Mm. And but his main theory is this concept that what we would call the non-local hidden variables. Oh, okay. And actually, Bohm inspired John Bell in who came up with the Bell test in the 1960s. That was the first test for entanglement. Mm-hmm. And the Bell test allows you to test to see indeed if these, two particles are correlated no matter how far apart they are, such that they're instantaneously changed when one is measured. And he was able to make a test for that. Now that test shows that you can't explain the correlations using, some parameter or variable about the universe that you just haven't measured yet that works locally.
Oh,
okay.
But because the particles are very far apart from each other.
But what David Bohm found was there is a possibility for non-local hidden variables. So you still have to accept this concept of non-locality, that things can influence each other no matter the distance between them. And then his theory led to this concept of what's called pilot wave theory, that basically the wave functions that govern quantum mechanics are not the end of the story, that there's a super wave function, that there's something that forms the wave functions. And the analogy he gives is a gamer. So you have a game and you have someone playing the game, right? And even within that, you have multiple kind of like if you start at kind of the hardware is guided by the software is guided by the gamer. And who knows, maybe the gamer is guided by something, and it just continues. And he, philosophically, at least, he considered many what he called super implicate orders that all influence the suborders. But that's a basic idea. You can see it gets really deep really fast.
Yes.
And I just love it. And I don't know much about it, but I just love it.
Yeah,
So, yeah.
Well, that's a great example. Yeah. Thank you. Yeah.
Thanks.
Yeah. Okay. So you alluded to the idea of using quantum communication to communicate between a lab and, say, a public space.
Yes.
Could you discuss the public quantum network that you have been a part of constructing? What's kind of the history and motivation behind the project, and what's the current status and future plans?
Yeah. So, this started when I had to write a grant proposal. So, when you start to lead a research group, you have to get money to fund your research group. And the proposal call said, think outside the box. Okay. This seems to be a theme. Anyway, and so I was like, okay. And I was somehow inspired by my dad, actually. So I mentioned my dad. He brought these personal computers for the first time into classrooms that he was teaching. And I was so impacted by that as a kid. I think that influenced why I was kind of techie growing up and why I loved to do research when I was an undergrad. And I thought, wouldn't it be great to do the same thing for the technology I'm working on now?
Yeah.
Like, wouldn't it be so cool if, I could bring that and see that development and start that development for quantum technology, just like for personal computers, and so the analogy, is, that we made is cell phones, so you start out with these really basic wireless communication devices, and then they're just phones for a long time. And then the more and more people were able to use them and start to code and think of ideas and start to, influence applications. Now they're just exploded in terms of what you can do, right? And so I was like, to do the same thing with quantum technology, which currently only has a handful of applications, like I said, very niche things like, if you can do this in this case and so on. Wouldn't it be great if more and more people were thinking about how to use it, and they came up with applications the scientists wouldn't even think of, because we're all stuck in the lab in the Copenhagen interpretation and not thinking of any new ideas. And so that was really the motivation. So I started asking around, and quantum networks, what they are is basically you have particles of light called photons. They are entangled such that measuring one changes the other. And you just send them out, you distribute them. And like I mentioned earlier, you can do communication that is, sensitive to eavesdroppers. So it can be really secure. If you know there's an eavesdropper present, you know that that's not secure. So you wait until they're not present and so on. And there are a handful of networks throughout the world, some varying sizes. The largest one is in China. And so I knew it was possible to build a network. And so you just need to identify, okay, what fiber optics are available. So I started asking, and it was one of those serendipitous things. Like everyone I asked was like, oh, you should talk to so-and-so. And that person would be like, oh, I know just the person. And it just built this network. And I ended up being led to the fiber optic network that was installed in 2009 from funding of the American Reinvestment and Recovery Act of 2009 that was meant to bring broadband internet service to underserved communities.
Oh, okay.
And, you know, in my vision, that's precisely what I wanted. I was like, I don't want to just keep this nestled in the, you know, ivory tower. I want to bring this out and get the ideas from the folks on, you know, in the real world out there. And what's great is this UC2B network, Urbana-Champaign Big Broadband. They were really enthusiastic because that's the vision they had for building that network to begin with. It would bring technology to people who don't typically get that technology first. Mm-hmm. And so enthusiasm was building and building. And we figured out which fibers to use. We figured out how to make the source so that it could work with those fibers and so on. And people were, I don't know, it was very, you know, certain times there's this idea and everyone just gathers around and just works together.
Yeah.
You know, it was amazing. Amazing students, you know, Paul Kwiat and his team, amazing. And then it's not, because it's public, the library, we went to the library and their Urbana Free Library. They're all about technology to the people, right? Mm-hmm. So they have computers with internet for people to come and use. And their theme is to provide things to the community. So they were also so enthusiastic and everyone had input. Place. And, you know, and when you go to the public, you have to explain things. You have to have, you know, artwork, icons, things like that. And just everyone came together. And so we got the technology working, and then we had our launch event. And, you know, it was standing room only in the library. So that showed us that people are wanting to learn more about this. Mm-hmm. People are excited, and there is a lot of potential there to do what I imagined, which is that to engage people. Mm-hmm. So that really continues to drive us, and we've made it fully automated. We're now going to install a second node at the library. So currently what people can do at the library is a Bell test, testing that the photons are entangled that we send to them from the lab. And, but, you know, that's very, you know, explaining that Bell test, you know, we're, what is it, an hour in? And we're still not there. So it's not, something that we expected people to be like, oh, we totally get every little piece of it. But we just wanted to kind of show, hey, this technology is real. It's in your library. Let's talk about superposition. Let's talk about entanglement. We want you to learn more. We're going to be continuing to do this, and we want to learn from you. And now we're getting to the point where we have 2 nodes. And with 2 nodes, suddenly you can do stuff that is much easier to understand. You can talk about sharing a message, you know, and how many bits of information you need to share the message, and how do you create the bits, and how do you encrypt it? How do you make it secure? Mm-hmm. You know, already that's pretty difficult to explain well, but it's like at a level everyone's kind of familiar with. When they send an email, they want to make sure it's secure. They've heard encryption. They've heard all these words. So anyway, we're really excited next year around February to launch that. And right now, if we make it, we plan February 15th, and it'll be Send a Quantum Valentine.
Oh, wow. That's so fun.
Yes, so yes. Cool. And we have different things people can do, but
and no one can read it because it will be encrypted.
Yes.
So no one will spy on your love life.
Yes. That's the whole idea. Yes. And yeah, so.
Yeah. So this is the second node, but currently if someone were just to go to the Urbana Free Library, they would be able to find the setup and make a Bell test.
And make a Bell. Yes, that's right. Okay, awesome. And then there's a little activity with a light table that shows superposition using polarizers on light, which are the basic elements of the quantum network. It's light and it's polarization and how we change it. And so it's all kind of, that's the great thing also about photons, that once people learn the word photon, which it's interesting, I don't think that photon is a generally used word. And quite often when I would say photon later, I would see in the article proton, because everyone knows protons. Yeah, but photons are not. And so I've now started to tackle that issue along with some amazing physics education researchers at UIUC, and trying to make a curriculum for middle school and high schoolers to start to learn these concepts young, to get that initial. And again, it's just, I think a lot of times people think science is kind of figured everything out. And it's exactly that box, except, you know, whereas for a physics PhD, the box might be Copenhagen. For a lot of people, they just think there's just not much else to figure out. Like everything's working like a machine. But it couldn't be further from the truth when you dig down deep enough to the quantum interpretation. It's clearly, that is not the way that we currently understand. That's not our best understanding. So why aren't we teaching the best understanding from the beginning?
Total sense. And teaching it to, or telling people that it's not a box seems to me to be a good way to attract creative people.
Exactly.
Who want to think about,
who want to push the envelope.
Yes.
Exactly.
Yes.
Please come.
Who when they hear that, they feel like that's the place for me, because I love to be creative and thinking about these sorts of things. And like I say, I think to welcome those people who might not be the ones that want to build the part, right? But they want to think differently. I think having physicists who are already immersed in that, on the different ways of understanding their experiments, could really amplify how many opportunities there are for people like that.
Yeah.
Because I don't think there are many opportunities. I think if someone came like that as a PI, I know, and I have certain projects and I need them to build something, and I'm like, yeah, you can think about that on your own time. I just want you to build this thing, right?
Yeah.
And I think quite often that's kind of what a PhD ends up being. So I'm trying to break that open for my own students. And I just hope that whole, I hope people embrace that more.
I feel like that's a fantastic point. Like, if we as physicists have the training to talk about the interpretations and bring other people in, then we'll just have more diverse applications. And I love the Public Quantum Network for many reasons, but it really reminds me of a point that Katie Ansel made when she was on the show. She is an expert in physics education, and she was talking about the importance of meeting your audience at their expertise and respecting their expertise.
Yeah.
Like, they might not understand the inner workings of the quantum network. Like, I don't understand the inner workings of my phone, even though I am a physicist. But I still can bring my expertise to the table and use the application for something new and exciting.
Exactly.
So by providing them with the technology and just acknowledging their expertise, being like, I don't have your expertise, but I would love you to use this in a way that, that kind of
that's fantastic. Yeah. And I think that basically is about openness.
Yeah.
And not thinking there's one way to do this. And I think we need more of that for sure.
Yes.
And I think one way to open that opportunity is by making it clear we are working within a certain understanding, and we should practice coming at a problem from very different perspectives. And so David Bohm actually tried to do what he called dialogue based on that. So Bohmian dialogue is basically saying you may not believe in that perspective, but take it as if you believe it, and then see what you learn about the problem.
Like a debate.
Yeah.
Like where you take the opposing side.
Yes. And so I think there's a lot of overlap of his ideas and like political theory, or even just social, how people think and make decisions. Anyway, it's really fascinating. Yeah,
that's fantastic.
I love how by networking between the lab and the Urbana Free Library, you not only networked that physically, you networked the people.
Yes.
That is so fantastic. So many networks built on so many levels.
Yes.
It's so cool.
It's all about networks.
Yes.
It's all about the village.
Yeah. No, it's so, and what it's generated in my team, like in the Public Quantum Network team, it's that connection. If we hadn't done that, we wouldn't be thinking of how to explain it. If we hadn't thought about how to explain it, we wouldn't have understood even what we do to that depth. And so it really is a feedback loop. And the public quantum network itself might get a one person a day, looking at it and trying it out. But I can't overstate the impact it's had on the research team that made it.
Yeah.
And I'm just hoping to see that come full circle so that more and more people have the impact from the public side. But I think to get there, we still need some technological improvements so that we can make it more interactive and people can understand it easier.
That makes sense. Yeah. Whenever I need to clear my head, I go for a walk. And this is kind of like having your lab group take a walk out into the community.
Yes. Yeah, that's right. It's a great analogy.
Yeah.
Yes.
Yeah, that's very true. We're all teaching each other.
Yes. Yeah.
So we're going to switch gears a little bit and talk about some advice you have. So according to the American Institute of Physics surveys, women are much more likely than men to make career compromises for family reasons. Do you have any advice specifically for women about finding a work-life balance?
Yeah. I think it's actually closely related to everything we're talking about because it has to do with what your perspective is on your work and to what degree it meshes well or not with the life that you imagine for yourself. And I think the more open-minded we are about what a successful career looks like, the more welcoming we'll be to those who have, a life structure that wouldn't typically be considered suitable for, let's say, hardcore research at a, university. So, that's just kind of at the community level. I think I think actually having the online abilities has helped a little bit.
Yeah.
So, during COVID, people couldn't go to conferences and a lot of people said, this actually worked well because now I could stay home with my kid more. And, but that was like where everyone was on even footing. So everyone had to be online.
Yeah.
And so that brief advantage was there for a while. But now I don't think it holds much advantage because there aren't many conferences that do hybrid anymore.
Yeah.
But the meetings, there are certain meetings and especially things like reviews of proposals, like panels where you have to meet with many people and talk about proposals. I think those have really benefited from the online, moving more and more online. So that's just something I noticed in my life. Like I could be at home more, especially during that critical time when, things were uncertain and that certainly helped a lot. So yeah, just being more aware of that and being real, kind of categorizing things that I can be online for that. I don't need to be in person for that because there's still some categories, like I mentioned, panel reviews or, things where you're providing a service in a way. And they say you could come in person, you could be online. So I think using that flexibility, I think is important. And so I think that's something relatively new that's come about. I guess that's one thought. I don't really have much to contribute that's different from the standard thing, which is you carve out the time for your family and you make it for your family, as much as you can. And there'll always be those exceptions, that meeting that just can't be rescheduled. But making people aware and bringing up the topic periodically and saying, hey, I noticed that these meetings happen at this certain time in the evening. Is there any way we could move that to a different time? And just always negotiating. And there's no like, I'm going to sit and everything's going to be great. You kind of always have to be constantly negotiating yourself and with others to make sure that you have the quality time you want with, the family you're building or that you have. So, and I think that's the case for everyone across the board, not just women. I think for women, one thing I've noticed is it's not so much that you are a woman. It might just be that the way you talk, the way you think, is different.
Yes.
Yeah. And I don't think it's just women. I think some men, there's a certain way of thinking, a way of talking, a language, and you learn that jargon, you learn that way of speaking, you learn that way of projecting confidence that doesn't necessarily feel natural to you. And you wear that suit and you wear that. And I'm just hoping that through bringing in this a little bit more loose perspective, saying, look, we don't have the we don't have the answers set. There are amazing things to be discovered with a diverse perspective. I think all of that kind of feeds into
absolutely
making it so people feel like I can talk like that. I can, I don't have to worry if I don't pronounce this just right, and I noticed this quite a bit. People, they're so smart, but they just haven't gotten that language or that, or they have an accent or there's just something, right? And then you can just feel there's this shift, like people don't take them seriously.
Yeah.
And, so, I don't know. It's always in my awareness and
yeah. I think just like, that is a great kind of like first step to take, though, just being aware that there is code switching, which is happening.
Exactly. Yeah.
Because I feel like my first year in grad school, I didn't have the language to say that I was code switching during class. And then kind of learning about that and learning that's something that you are performing and that, it doesn't have to be that way.
Yeah.
I feel like it's very helpful to acknowledge, because I feel like in physics, we're not quite there yet
No.
to admit that we are code switching when we go into work.
Yeah.
And so I think that's a great step, just kind of talking about that, because that kind of, loops back into everything. Like you're saying, like if we don't have to code switch, people will feel like they can bring their full selves to work, like women included, like historically marginalized folks, and that helps with kind of the work-life balance if you're not being so drained at work.
Yeah, and I think it comes from an honest intention, which is efficiency. It's more efficient if we all talk the same, look the same, act the same. It's just more efficient. But to have what Katie Ansel said, to appreciate that everyone brings something unique and potentially useful and even, field changing. It requires a looseness and creativity will not thrive in an environment where things are done a certain way and that's it.
Yeah.
So, I think my hope is that with all of this wave of interest and funding and so on in quantum, that at some point it reaches a crescendo and everyone's like, that's as much as we can do. And then it's just like, it opens up and says like, we can do, there's ways to do things differently and more and different and better. Anyway,
that's great advice. We appreciate that.
Yeah.
So you also mentioned that you had made some kind of changes to your advising style post-pandemic. Could you kind of talk a little bit more about that?
Yeah, I mean, certainly along those lines is seeing the person more and more and more. And I think I definitely fell into that trap of efficiency and believing that, an efficient meeting is a meeting where you just talk the language and that's all you do during that meeting. But I saw how everyone was struggling. And so we set aside one group meeting a month. We were meeting weekly. We set one group meeting a month aside to talk about anything. And the topics that students chose were racism in STEM. They were women in science. It was a moment to breathe and just, do Bob Ross paintings together for an hour. And, just stuff like that. And I want to say we've continued it, but I just realized we relapsed a little bit, but it made a real impact. And the group dynamics softened. People spoke up more that were more reticent before.
That's great. That's great advice. Because I'm always trying to think about how to do that.
Yes.
For folks who are more reserved.
Yeah. And it started to permeate everything because once you open that door, then you can't treat people the same anymore. You start to care. Oh no, I care about this person now. Oh no, it actually I want to make their life better. I want to make their work environment. I want everything to go smoother for them. And not that I didn't do that before, but I saw it as almost a mathematical equation that was limited to, this is the goal and this is how we get there. And so,
which is very, very common in this field. So
right.
It's not any fault of yours.
Right.
This is very much like the culture of what's happening.
Yeah. And it may be also the point in my career where I have the room to be that way because I have tenure.
Yeah.
I'm a full professor. I don't have much to lose. But what I found is I gain. I don't lose at all. In the long run, I totally gain because what happens is I look at the student. And like Katie said, I find things that they bring that are so unique. Yeah. And then I kind of let them guide more. Mm-hmm. I'm not like, go and do this, this, and this. Instead, I say, oh, that's interesting. What do you think? And then they'll think differently than I do, but I'll see value in that and realize they're probably thinking that way because they maybe lean to do that first or they lean that way in some, and then of course I won't just let them go willy nilly. I try to guide them, right? And I say, well, if you go that direction, then something might happen, but I'm definitely have a more open style and it's just everyone feels like they have a say. Yeah. Everyone feels engaged. And with this public quantum network, when I really opened the doors wide, I was like, listen, we're going to do something totally, then everyone was like, really, it's super, super engaged. Oh. And, working those hours that, everyone wishes they could drive harder, right? They're working those hours because they love it.
Yeah.
And I can't manufacture that. Mm-hmm. And I see so clearly the two ways of doing things, top down, bottom up. It's like totally, it's got to be integrated, diverse, organic. It has to be happening from people's own intuition, own inclination, own thoughts versus just do the work.
Yes. And I really like that because I think so often working in a group, people can get annoyed at people's differences.
Yes.
It's the different things about other people that, there's a lot of tension between. But then as soon as you start to kind of break down those barriers, they start to appreciate the differences.
Yes.
And that's when the people in the group can really start to thrive. The dynamics get so much better.
Oh, yeah.
Because people really are like, oh, this person has these skills that I don't have. They know these things that I don't know.
Right.
They are able to grind through these specific things in a way that I cannot.
Absolutely. Absolutely. And honestly, I think it does take more time and work maybe up front to build that structure because the fact is people do have to do the foundational learning to be able to contribute at a level that is good for the whole team. Yeah. And so, but to make that contribution, just telling them to do it is not as effective as saying, hey, why don't I work with you on that for a bit? Why don't you team up with this student? And you just think of it differently than just repeatedly saying, just do this, right? And you kind of try to give them more autonomy right up front, right at the beginning, even for the tasks that are only preliminary to actually doing what they need to do. Because as you know, you go in and as a student and you don't know much, right? You've got a certain level of your training from classes. And then the lab environment, there's just so many places you could go astray. Mm-hmm. So I wouldn't say it grows on its own at all. It's like a garden. Okay. Yeah. You got the plants, you got the weeds. You got to put the stinky fertilizer every so often and you just have to tend it. Yeah.
No, it makes, from an advisor perspective, there's I'm going to tell people what to do. But kind of the method I see that you're proposing or you're talking about is more, I have to listen.
Yes.
That is resource intensive.
Yes, absolutely. Yes. I spend a lot of time listening. I'm in meetings all week. But that's what it takes.
Yeah.
So, yeah.
I heard from an anthropologist once who was going to do field work with the community. They said, how do we put in the grant that we have to go hang out with them first?
Yes.
You have, how do you have to carve
exactly
out that time for relationship building.
And it won't be successful unless you do that, right? Yeah. And that's exactly what I'm finding with the Public Quantum Network is that we are considered outreach. And often I feel like it's an easy categorization to make. You're like, outreach, not research, but the public quantum network is both.
Mhm.
And they're intertwined in a way that's impossible to undo it.
They're entangled.
Entangled. Yes. Very good. Because, what protocol we do depends on what people might interact with. And then how we do it will depend on, so everything is in our meetings. We're constantly doing this. We're constantly like thinking about the interface, then thinking about the technology to make that interface happen.
Mhm.
And then thinking about the technology that would make interesting research and thinking about how to apply that in the public space. So it's like always together. And so, that's another element of public quantum network. I just hope is like, might be an inspiration for researchers who want to do more fluffy. No, I wouldn't call it fluffy, but some people would call it fluffy.
Yeah.
Right?
In physics, we would tend to say things that are kind of more social science oriented would be deemed fluffy, but
Yes.
they're actually both equally difficult.
Yes, they're absolutely. And I think the physicists, there's a certain pride
Yes.
that we're the hard science.
Yes. Katie called it
And-
epistemic trespass.
Oh,
Yes.
wow. Okay. Yeah. So, and so I'm kind of pushing those boundaries, I feel, a little bit through this work. And, it's kind of become the thing I talk about with like funding, program directors and so on. I'm thinking of it like this, it's really a meshing of the two. And I'm getting really positive feedback because I think that's what NSF and other funding agencies, that's what they hope to see, right? When they say broader impacts, they really hope that, that research has a real influence on, and it's hard to do, but I think quantum networks, by their very nature, that the fact that they're networks, they actually physically bring different people together. It's a great way to show how that can happen.
Yeah.
Yeah.
Yeah, that's fantastic. And I also really hope that this project inspires other researchers to kind of think outside of the box in terms of outreach, that they're not distinct from each other, that we actually can really help each other develop. Like public and scientists.
Yeah. And I think, it's specific to the quantum research as well, because it's so technology driven right now. Quantum technology is kind of the goal. Mm-hmm. And so I think interfacing more and more with that public aspect is kind of an important aspect of that. Yeah.
Yeah,
Mm-hmm.
absolutely. Yeah. Yes, so we've right into the last question.
Mm-hmm.
So in physics, emergence is used to describe a behavior which occurs at large scales, but not at small scales. In other words, for an emergent system, the whole is greater than the sum of its parts. For example, when blackbirds flock together, the group will move and bend in a way that the individual bird does not. Can you give us an example of emergence from your work or just kind of general life experience?
Yeah. I mean, it happens every day. Thanks to these amazing students that I work with. And it's both undergraduate students and graduate students. And I think a lot of it has to do with the listening aspect, that you can't have an emergent phenomenon if they're uncorrelated and not listening to each other, somehow interacting with each other. So I think that, again, using public quantum network, but actually all of my research projects, there is this element of an idea is spoken. It is not immediately, turned down. It influences the discussion, and that leads to a different way of doing things or a new project. And, I've really been fortunate to work with graduate students who have both the kind of technical and kind of strong academic foundation, as well as the creative element. And this has defined my research program to a large extent recently. Mm-hmm. Of course, thematic guidelines. And of course, I feel very much that I am a part of an integrated whole. Mm-hmm. And I'm so excited to be a part of it. And I think that just, that continues to strengthen that, that back and forth and just appreciation. And, so I think that's kind of what a research program should feel like. Mm-hmm. So I feel, very lucky to be in that mode right now.
Yeah, that's fantastic. That's awesome that you were able to kind of get to that place and build those relationships with your students. Because it definitely takes work. As we touched on. So
yeah, and the things that you can appreciate are a gift. Appreciation is absolutely a gift.
Yeah.
Oh yes, yeah. I mean, you know, what is appreciation, right? It's like taking that moment and seeing the other and just being glad that you're working with them. And that's not something that we're ever taught. You know, faculty and you know, principal investigators for grants and so on, they aren't trained to do that.
Yeah.
And so we're all just groping our way. We're just finding our way with, usually it's based on what our advisor did for us, right? How did our advisor run the group? And then what we observe amongst our peers on how they're doing things.
Yeah.
And there are a few, you know, and it's interesting as you talk with people, certain examples, they just kind of brighten up. You're like, I didn't really think of doing that way.
Yeah.
And so again, networking, spreading that concept and that appreciation, I think is important, and just talking about it.
Yeah. I mean, it's like, it's a good way to develop your inner world and develop the outer world. Like, even in this podcast, I appreciate Maddie. She's very extroverted. She's really good at talking to people. I watch her talk to people all the time, and I learn so much.
Yes.
Just from, I'm going to gloat on that.
That's very sweet. Yes. And Katie made, that's a great point that we are, especially in physics, we're not always operating on the joy of our connection with others.
Yeah.
And I feel like another thing that Katie Ansel said was like, isn't that like a beautiful thing that we all can like bring our own individual skills to a project, that we don't have to do it all? Like, isn't that so much better than if it were to be the other way around, if we each had to do it all?
Right. Right.
Yeah.
Yeah. Well, we could go on, but I love it.
Yes. Yeah. Well, I think that's a wonderful way to end.
Yes, that's a great way to end. Thank you so much for joining us.
Oh yeah, thank you. It's a pleasure.
For further readings and resources about the topics covered in today's episode, check out the links in the description. Thanks for listening and stay connected.